Okay, so we are going to get started and talk about how we can use what we know about the standard normal curve and what we've learned about it and apply that to other normally distributed populations. So to begin, the first thing that we need to learn how to do is to convert what are called X values, or random variable values, into what we call standard scores, or most of the time we usually refer to them as z-scores. And the way that we do that is we use a formula. Z is equal to the X value, or the raw score, that's also referred to as a raw score, the X value, minus the mean of the population, divided by the standard deviation of the population. So be sure that you have this formula handy as we go through the notes for this. The first example that we're going to do says that the time it takes for a pizza delivery is approximately normally distributed. You have to actually be told that your variable is normally distributed or not. And it has a mean of 25 minutes. Which means the center of your curve is at 25 minutes. And it has a standard deviation of 2 minutes. So that's your population standard deviation of 2 minutes. And what that means is that each one of these little 6 chunks under that curve, that's a value of the standard deviation, so each one of those marks off 2 units. So what that means to us in terms of our delivery times is that this delivery time is 25 plus 2, which makes this one 27. And then the next one up is going to be 29, because that's the value of the mean plus 2 standard deviations. And then this last mark is 31, because that's the mean plus 3 standard deviations. So that will be 25 plus 3 times 2. And then on the other side of the curve, the same thing happens. This first mark is going to be the mean minus 1 standard deviation, and 25 minus 1 times 2 is 23. And then if I go down another standard deviation, That's going to be the mean minus 2 standard deviations, which will be 25 minus 2 times 2, or 25 minus 4, which means this is 21. And then if I go down the third standard deviation, that will be 25 minus 3 times 2, or 25 minus 6. So this would be 19. Okay? And since both of our examples use that same curve, I'm going to go ahead and slide this up and go ahead and label the other curve underneath that. So this is 19, 21, 23, 25, 27, 29, and 31, and that's all based on the mean and standard deviation of 25 and 2 respectively. Okay? Now I want you to keep in mind that these correspond to z-scores. The z-scores are always given to you in these little pieces of the formula that I used. So for every one of those raw scores, and that's what we're going to actually wind up calling them as raw scores, there are also z-scores. There's our z-values. And these values are the x values, but they occur at the same place on the curve. So the first question they ask us is to convert 21 minutes into a z-score. Right, exactly.
Which is maybe 2.
Mm-hmm. That's actually all it's asking for. And remember, z-scores do have 2 decimal places, so I changed that -4 over to exactly -2.00. So what that's telling us is that our z-score of -2 will tell us where 21 minutes falls on the curve. Because it's 2 standard deviations below the mean of the curve. Okay? So all we're doing, we're not finding probabilities at this point, we're just converting. We're just changing a raw score, an x value, into a z value so that we can locate it on the axis of that curve. And that's all we're going to do on the second one as well. On the second one, it tells us to convert 29.7 minutes into a z-score. X is going to be 29.7. So then we're going to use the z-score formula by taking x minus mu divided by sigma. So x is 29.7, mu is 25, sigma is 2, and we'll have to do a little bit of arithmetic here. So I'll get our handy dandy calculator and clear it off and do 29.7 minus 25, and then divide the result by 2 and get 2.35. And this is a positive z-score. So by the fact that it's positive, we know that it's going to be to the right not the left of the mean. So at 2.35, that's somewhere between 2 and 3. And notice that 29 is right here, and 29.7 would only be a little ways up from there, about maybe a third. So be sure that you understand that those two are actually the same thing. Those are saying the same thing. Z is equal to 2.35, X is equal to 29.7 in this problem. Okay? So when you calculate a Z-score, the purpose of calculating the Z-score is mostly just to locate your X value on the horizontal axis of your curve. So now we'll do an application problem. And our first problem says the weights of adult rhesus monkeys are normally distributed with a mean of 15 pounds and a standard deviation of 3 pounds. So we've got a mean. And we have a standard deviation. And we have the information given to us that they will be on a normal curve. They're normally distributed. So that tells us that the way that we need to mark the curve off is to put 15 in the middle, because that's where the mean is. And since the standard deviation is 3, then 15 plus 3 is going to be 18. 18 plus 3 more is going to be 21. And 21 plus 3 more is going to be 24. And then 15 minus 3 is going to be 12. 12 minus 3 is 9, and 9 minus 3 is 6. So what that has told us in terms of rhesus monkey weights is that almost all rhesus monkeys weigh between 6 and 24 pounds. And a majority of them, about 2/3 of them, weigh between 12 and 18 pounds. And this again, while those are X scores, X represents the weight of a monkey, they have corresponding Z scores. And then the question that they ask us actually this time is a little bit different, because what they ask us is, what is the probability that a monkey's weight is less than 13 pounds? So the question they're asking us in symbols is to find the probability that X, which is a monkey weight, is less than 13. Now we can make a fair guess as to where 13 is, because 13 is somewhere between 15 and 12, and it's actually closer to 12 than it is to 15. So 13 pounds should be along about here. Should be right about there. And we're finding the probability that the monkey weighs less than that. We're going to be going to the left of 13. And that would be the yellow area that I shaded in under the curve. Now the way this actually works is we could find the probability using the z-score. We would convert 13 to a z-score. I'm sorry, I put X, but that should have been Z. So Z, since it is not a nice fraction, -2 divided by 3, if you do that on your calculator, you're going to get 0.6666 forever. And we're going to have to round that off. And we're going to round it off to 2 decimals and say that it's 0.67. So that's the same as the same line. That's the same line as we marked off with the 13 pounds. All that's telling us is that this line is about two-thirds of a standard deviation below the mean, less than the mean. So there's actually 2 ways we can answer the question. The first way we can answer the question is we can calculate with a z-score, because the probability that x is less than 13 is the same as the probability that z is less than -2/3 or -0.67. Those two should be the same because it's the same area that we're talking about. So first I'll calculate what is the area to the left of a z-score of -2/3. So we start out at -infinity, remember, because we're going from there up to 2/3. And our -infinity is always going to be -1 times 10 raised to the 99th power. And so that I don't have any round off error, you could put in -0.67, but so that I don't have any round off error, I'm going to put in -2/3. And then the mean of z-scores is 0, and the standard deviation is 1. And we see that the answer is 0.25249. So we're going to call that 0.2525. So that means there's a 25.25% chance that a monkey selected at random would weigh less than 13 pounds. But because of the relationship between the x's and the z-scores, we could also do this by calculating this. Now we're doing the same thing. Get that up there where you can see it a little bit better. Below is still -infinity because, well, okay, realistically, monkeys' weights don't go down to negative anything. Realistically, the smallest monkey would weigh 0 pounds, which means there wouldn't be a monkey there. So realistically, we could start at 0. But the thing is, the smallest monkey weighs 6 pounds most of the time, and even if we go down to 0 pounds, that's another 2 standard deviations down. And if we go on down to -infinity, once you pass the 6-pound monkey, there's really not much area left under the curve. So these answers are going to give us, pretty good results, whether I use -infinity or if I use 0, which is the logical smallest weight that we could have. So again, we're going to go normal CDF, and I will work at first with negative infinity, going up to 13 pounds, with a mean of 15 pounds for all of the monkeys, and a standard deviation of 3 pounds for all of the monkeys. And notice that you get exactly the same answer that we did before. That answer didn't change. If you round it off to 4 decimals, it's 0.2525. And if I change it and say, well, you know, realistically, there's not going to be a monkey that has a negative weight, and I just change that bottom number to a 0 to put it in, you know, more realistic terms of the monkeys, I'm still getting 0.2525. Notice the only place that there's any actual real difference is after you pass the 6th digit after the decimal, which is practically no difference at all. We would still get the same answer. Okay? So what we're doing with this formula is we're actually using the z-score formula to locate where our boundary values are in terms of the x-scores. We're able to put it in the right place. Because the monkey weight of 13 pounds corresponds to a z-value of negative 2/3 of the standard deviation below the mean. Okay? Those are all tightly connected to one another. They mean the same thing. And then the one at the bottom of the page, we're talking about the same situation, so I'm just going to copy down the weights of the monkeys. So we're still talking about the exact same curve that we were talking about before. But this time, what they ask us about is what is the probability that the monkey's weight is between 12 and 17 pounds. And it just so happens I don't even have to find the z-score for 12 because 12 kind of finds itself. I'm exactly 1 standard deviation below the mean. So I didn't need to do the formula on that one. But now as for 17, 15, 16, 17, my 17-pound monkey's going to be along here somewhere. And that one's not an exact place, so I'll calculate the z-score for 17. And this one turns out to be positive 2/3. Or about 0.67. So I can find two different things. I can find the area under the curve, between a z-score of -1 and a z-score of 0.67 or of 2/3 if I want to be exact, since it doesn't come out even and I don't want to round off. And the mean of the z-scores is 0 and the standard deviation is 1. So that's one way I could do it. But I would get the same answer if I do it this way. And just use the mean and standard deviation of the monkey's weights. And I should get the same answer either way. And as long as I don't round off any numbers, I don't round 2/3 to 0.67, I do get exactly the same answer. And that's the area between those two values under the curve. So that's 0.58885, which we will round to 5889. So that's that shaded area is 0.5889. Does anybody have any questions? Does it make sense? Okay, let's try a couple more. This one is the pediatrician that has the 3-year-old patients, and she has 200 of them. That's not a sample because it tells us in the problem every patient was included. So she has a total of 200 patients. So that's her whole population of 3-year-old patients. And they give us the information that the mean height for those 3-year-olds is 38.72. And the standard deviation of those heights, which is sigma, is equal to 3.17. And the question that they're asking us is, what percentage or what is the probability of a 3-year-old female patient that has a height, which is X, less than 35 inches. So this is what we're trying to find, the probability that X is less than 35. And once again, the mean is 38.72, so we'll put that in the middle, because its corresponding z-score would be 0. And each one of those little additional marks, this distance right here, is 3.17. So just to give us a rough estimate of what all these weights are, I'm going to actually label in the curve. So the smallest patient of all weighs 29.21 pounds. And then the next markup is 32.38 pounds. And then up one more is 35.55 pounds. And then the next one should be the mean, and it is. So then I'll go up three more and label those. 41.89. And 45.06. And 48.23. So we know that virtually all of her patients weigh between 29 and, or 29.21 and 48.23 pounds. So if she were to have a 3-year-old patient that weighed 50 pounds, that would be very, very unusual. And by the same token, if she had one that only weighed 27 pounds, that would be very, very unusual. Oh, I'm sorry, that's not pounds, that's 27 inches tall or 50 inches tall, let's say. Those would be unusual. So 99.7% of her patients are between 29.21 inches and 48.23 inches tall. Okay, we always want to try to think about what this means in context. Now, as for the ones that have a height that's less than 35 inches, 35.55 is right about here. So 35 inches exactly would be a little bit to the left of that. And since it says what is the probability their height is less than that, we're looking for this area. So the probability is probably going to be small. It's not going to be like 0 or anything, but it's going to be a smaller probability. So in order to find this, you can do normal CDF, and realistically, even though this goes all the way down to negative infinity, we know that 0 would be the smallest weight actually possible. So we can put in the 0, or you can use the negative infinity, and go up to 35 with a mean of 38.72. And a standard deviation of 3.17. And if you wanted to be sure you located that 35 exactly where it was supposed to be, we could calculate its z-score. And get negative 1.17. And you can see that this would be a negative 1 right here at 35 and negative 2 here. So that is just a little bit further from 0 than negative 1. So that means that this is equivalent to doing this. If we did both of those, we should get the same answer. So let's see how close we get. So with the z-score, we get 0.1210. And if we use the more realistic bottom number of 0, up to 35 pounds, with a distribution that has a mean of 38.72 and a standard deviation of 3.17, we get 0.1203. So there's just a little bit of difference. But there's not enough difference to actually worry about which way you're going to calculate it, because what I want you to do on a problem, on a test, or on a quiz, when we take the test, it's okay to calculate the z-score and do this and tell me that's what the answer is. It's also okay to do it this way unless I ask you for the z-score. It's okay to do it this way and tell me that's what the answer is, because this is actually a more accurate answer. This is a more realistic answer, okay? But you can do either one. Just be sure on the test, I'm not grading answers, I'm grading your work, okay? Even if I give you a multiple choice question, I'm going to ask you to show me how you got the answer you picked, because I need to see that you know how to do the problem. That's the most important thing. Now, we had problems with z-scores where we had to go backwards. We had to do inverse norm. We also are going to have the problem of, if we got the z-score, in this case, since this is an application, if we have the z-score, can we go back and find the actual raw score? That's the x values. The raw score is the weights or the heights or the pizza delivery times. Okay, those are the raw scores. And we can get those back from using a formula that's based on the z-score formula. I could work through the algebra and show you how the z-score formula turns into this formula, but I'm just going to give you the formula. The formula says you can find the raw score the x is the raw score, by taking the mean of the population and then adding to it the value of the z-score that they give you times the population standard deviation. And realize that when we're doing this, it's going to make a lot of difference to us whether or not the z-score is positive or negative, because if the z-score is negative, we're actually going to be subtracting from the mean rather than adding. But we're still adding a z-score, it just would be a negative z-score in some cases. So this problem tells us, find the raw score associated with a z-score of 1.60. If the mean weight of the item is 35 pounds, So that's mu. Oops, I'm drawing a line to the wrong place. So that's mu. And a standard deviation of 2.8 pounds, that's sigma. So this is how we would find the raw score from that information. Our raw score, which is X, would be the mean, which is 35, plus the z-score, which is 1.60, times the amount of the standard deviation, which is 2.8. So we just need to do some arithmetic. And our raw score turns out to be 39.48. And then I can confirm this by putting the mean on the curve and then add standard deviations. 35 plus 2.8 is 37.8, plus 2.8 would be, let's see, I don't trust myself this late in the afternoon doing arithmetic, so I won't. So that'd be 40.06. And 43.4. And then here's my other values, 32.2. 29.4 and 26.6. So this corresponds to z-scores of -3, -2, -1, 0, 1, 2, 3. And our z-score was 1.60. And we need to convert that into the raw score, and when we did, we got 39.48. And 39.48 is more than 37.8, but it's less than 40.6, so that kind of confirms that we were right. So use the pictures to help you to make sure that you're doing the problem right. You should be able to confirm your answers with a visual. You're probably sitting there thinking, well, why would I need to do that? Well, let's talk about the pediatrician again. Okay, not the monkeys. Leave the doctor's office. Here we go. This was the pediatrician's curve. I'm just copying that off the same information we had earlier. So here's our mean. It says the heights are normally distributed with this mean, 38.72, I'm sorry, standard deviation 3.17. What height marks off the lowest 10% of her patients? Well, the lowest 10%, I hope obviously, is going to be in the bottom part of the distribution. So in order to figure out where that is, we need to find the z-score. So that the probability of whatever we have is less than that number that we're going to find is going to be the percentage. So we're going to have to use inverse norm. And an inverse norm, remember, we always need the area to the left, and that's going to be the lowest part, so we've got what we need. And the mean of the z-scores is 0, and the standard deviation is 1.
Did you not just put point 10?
Yeah, you could put 0.10. I just know that you're used to putting in 4 decimal places, so I left them on. But yeah, that's fine. You could actually even put in 0.1. As long as you're not answering a question for the computer to tell you, no, that's wrong, I said 4 decimal places. Just be careful if it's a MyLab problem you answer the way you want, that it wants you to. So here we're going to go inverse norm. With 10% in the lowest part of the curve, with a mean of 0 and a standard deviation of 1. And it says the z-score is negative 1.28155. And if we round that off to 2 decimal places, then that's just negative 1.28. And then we also know that sigma is 3.17.
Why did you use 0 and 1 instead of the 38.72 and 3.72?
You can. I'm going to show you how to do it that way too. Just like we could before with normal CDF, we can do it with the z-scores, or you can do it with the actual problem base.
Care which one is
I
it?
don't care as long as you show me which one you did. Yes, ma'am.
What process is this supposed to use the inverse norm or the normal CDF?
Because it gave us a percentage. Anytime they give you the percentage, you've got to go back. Okay, if they give you the probability or the area, then it's inverse norm. If they ask you for the area, then it's normal CDF. So here we've got a mean, 38.72. We've got a standard deviation, we've got a z-score, and now we can calculate the actual height, which is an x. So our x is equal to the mean, which is 38.72. Plus the product of the z-score, which is negative 1.28. And the standard deviation, which is 3.17. And we'll just do a little bit of arithmetic. we get 34.6624. So that patient would be about 34.66 inches tall, and that would put that patient shorter than the 35.55 inch patient, but taller than the 32.88 or 38 inch patient. So somewhere along here, that's the weight, but this is also the same as a z-score of negative 1.28. So what I'm showing you here in class right now is not necessarily exactly what I want you to do to work the problem, although I do want you to show me as much work as you can. But I want to make sure that you keep all of this connected in your mind, how it all works together. Now, in response to your question, yes, I could have done that in a little bit different way. I could have gone straight from the information they gave me. So if I wanted to do that, then I would do, it'd still be inverse norm, but instead of finding the z-score, I would use the mean of the problem, which is 38.72, and the standard deviation of the problem, which is 3.17, and I should get the same score. And if I'm rounding, I do. Remember, I rounded off my z-score earlier, so the answers are not perfectly in agreement. But if I round 34.657, I'm going to get 34.66. So that is going to be the same exact thing. So once again, I don't care which way you do it, but show me how you did it. Show me if you calculated the z-score of what it was and what the formula said. Show me if you use normal CDF with the problem information, what you put into the command, so that if maybe you just transposed a couple of digits or something, I can tell that that's what threw your answer off. And then I won't count it completely wrong. But show me how you did what you did. The how is much more important than the end result. Okay? Any questions? Okay, paying attention to the snow outside, I think instead of us taking a break, I think I'm just going to end this up a little bit early. So now we're going to talk about something called sampling distributions. Let x be a variable with a normal distribution, and the mean is mu, and the standard deviation is sigma. We're going to let x bar, and x bar is a sample mean. X bar is the sample mean that corresponds to random samples of some given set size, size n, a specified sample size taken from the distribution. What the theorem tells us, and I'm going to lead you through a little example to make sure you understand this, is that the x bar distribution is a normal distribution. The mean of the x bar distribution is mu, which is the same mean as the original population's mean. And the standard error which is a type of standard deviation. Of the X-bar distribution is the population standard deviation, but it has to be divided by the square root of the sample size, which is n. Okay?
What was the word after me?
After
On the first one, the length of the X-bar distribution.
standard error, now to kind of give you the idea of what we're doing here, let you follow along with me. Suppose I have two dice. Basically, those two dice represents a population of values where if I roll any of those dice one at a time, the members of the population are one of these numbers. And because of what you know about probability, if I did a probability graph, or something called a probability histogram, that's what it would look like. That distribution I just drew is a uniform distribution. Okay, it's a uniform distribution. And I'm not going to go through all of the different pairs, but I am going to ask you, if my first roll, because I'm going to roll these dice twice, if my first roll, which is represented by the red, is 1, 2, 3, 4, 5, 6, my second roll might also be a 1. And if that was the case, I would have rolled a sum of 2 using 2 dice, which means that X bar, that sample mean, would be 1. And similarly, if I rolled a 1 and a 2, then that roll would be called a 3. 2 plus 1 is 3, divided by 2, which would give me a mean for that roll, a sample mean of 1.5. And if I rolled a 1 and a 3, then that would be a roll called a 4, because 3 plus 1 is 4, divided by the 2 rolls would give me a mean of 2. Okay? Now, we could sit here and make every single possible dice roll. We could do that. We'd be here a while. Okay? We don't want to do that. Given that we're talking about rolling a die twice, how many potential outcomes are there on the first roll? There are 6. When I roll the second time, how many potential outcomes are there? There's still 6, because the die doesn't remember. You don't get to hold back. Which means that because of the multiplication rule we learned back in chapter 4, that means there's 36 different possible rolls, which means there's 36 different possible samples. Okay, there's 36 different samples. We don't want to have to write them all out. What I want you to pay attention to is what and trust, take this on faith for me, please, because we don't want to do this. The lowest possible mean is 1. And there's only one way that it happens. And that's if I roll a pair of 1s. Okay? The highest possible mean is 6, and that only happens if I roll a pair of 6s. 6 plus 6 is 12, and that's divided by 2 would give me a mean of 6. And there's only one way for that to happen. So that's 1 out of 36. There's actually 2 ways to get a 1.5 mean. Because I can roll a 3 and a 1, or I can roll a 1 and a 3. So there's 2 different ways. That makes it 2 out of 36. I think I said a 3, I meant a 2. 1 and a 2 and a 2 and a 1. If I roll a 1 and a 3 or a 3 and a 1, my mean is going to be 2 because that's a sum of 4. But I can also get that one more way. I can also get that if I roll a pair of 2s. 2 plus 2 is 4 divided by 2. So there's actually 3 ways to get a mean of 2. Now the others are going to follow this pattern. I got a little carried away there, so I'm going to move my 1 over 36 down. So what actually happens is there's 4 out of 36 ways to get a 2.5. There's 5 out of 36 ways to get a mean of 3. There are 6 ways to roll a 7. 7 divided by 2 is 3.5, so that means the sum was 7. You can get a 4 and a 3 and a 4, a 1 and a 6 and a 1, a 5 and a 2, or a 2 and a 5. So what happens is my distribution starts out low, peaks over the mean of 3.5, and then drops back down, and that's going to be a normal distribution. So this is the probability distribution for all of the possible samples of size 2 out of that population. And it has a normal distribution. The reason that that's important is because it leads us to something called the central limit theorem. If the original distribution is normal, even though we started ours off and it wasn't, if the original distribution is normal, then the sampling distribution will also be normal. The mean of the sampling distribution is going to be called mu because it's a population, but it'll have a little X bar after it because it's a population of sample means. So it's the mean of the population of sample means, and we're going to get tired of saying that real quick, so we're just going to call it mu X bar. Mu tells us it's the population, and X bar tells us what the population is made up of. It's always going to be equal, however, to the original mean of the original population. So if we know this, then we'll know this. The standard deviation of the sampling distribution has a symbol. It's called sigma because it's a population, and X bar because it's made up of sample means. This is what it actually is, but in order to keep us from being confused, notice that we'll also sometimes see that called the standard error. Okay? To find it, you need to know the population standard deviation and the sample size, and divide the population standard deviation by the square root of the sample size. So the standard deviation of the sampling distribution is called the standard error. And some textbooks actually use this abbreviation for it, but I don't think that yours uses it. Now, since we've been doing normal probability and we're saying all of this is normally distributed, we would need to know how to calculate a z-score. It's really not any different from what we had before. Except now we're not talking about just individual raw scores, we're talking about sample means. So that's going to be the mean of the sample means divided by the standard deviation of the sample means. And this are the same thing. And this is calculated by doing that. So that's your new formula for a z-score when we're doing sampling distributions. It works just like the old z-score. So we're going to work an example, but we're going to work it both of the different ways that we've been working problems. The first one is like what we've been doing. The time it takes to drive between cities A and B is normally distributed with a mean, that would be mu, of 14 minutes. And a standard deviation of 2.2 minutes. And I hope I labeled the bottom half of that correctly. I'm not going to swear I did because I did it in my head. And then we have our question, our standard question. What is the probability that, and I want you to pay attention here, it says a trip. One trip takes more than 15 minutes. In other words, what is the probability that X is greater than 15. Okay, here's 14, here's 16.2. 15 would not be very far from the center. So the probability that we're looking for is going to be less than 50%, but not a whole lot less. Because we're looking at almost half the curve. Now you can do this with finding the z-score, like I showed you the last part of the lesson, or you can just go straight to the problem, which is the way that I'm going to do it. So normal CDF, the low is 15. The high is going to be infinity, which I guess means you'd never get to city B. The mean is 14, and the standard deviation is 2.2. And that probability is 0.3247. So, everybody good with that? That's the same problem we've been working all along, all the lesson today. But now we're going to change gears. I'm going to keep this handy because we're going to compare it in a minute. This one sounds the same. Normally distributed, mean for 14 minutes. Tells you mu is equal to 14. And a standard deviation of 2.2 minutes. But before I go labeling my curve, I need to read my question. What is the probability that the mean time of 9 trips? I just got 2 pieces of information there. 2 very important pieces of information. X bar, not X. The sample mean, the mean time. The other one says find the probability that a trip, 1 trip. This one says find the probability that the mean time, X bar, of 9 trips. Is more than 15 minutes. When they tell me this is what happens. If they give me a sample size, I have to use the sample size. This is not just mu, this is mu X bar. And I'm not going to be able to use just sigma, I have to use sigma X bar, which is sigma over the square root of n, and in this case that's 2.2 over the square root of 9. And because I've already calculated that today, once before, that's about 0.73. It rounds off to 0.73. So instead of using a standard deviation of 2.2, I'm using a standard deviation of only 0.73. So this is what my curve looks like. So the top value on this curve is 16.19 minutes, and that's a mean. Now I can go down too, but I'm not going to do that in my head, because I know I'll mess that up. Well, let's just call it 0.73. This is going to be 11.81 and 11.08, and the bottom value is going to be 10.35. So there's the sampling distribution. I want you to compare that to the population distribution. This curve starts at the bottom at 10.35. Population starts at 7.4. The middle is the same. But the top value here is 20.6, here it's only 16.19. Okay? The difference between these two curves, and you can see it visually here, this curve is shorter and more spread out. This one is taller and skinnier because we're using sampling distributions. So sampling distributions are always going to be taller, skinnier normal curves. Okay, they're not going to be as wide. So when we answer this question, what's the probability of that the mean time of 9 trips between the cities is more than 15 minutes? Look where 15 minutes is. Look at how little that area is compared to the area last time. Okay? It changes your probability significantly, and what causes it to change is the fact that you're using a standard error. Standard deviation divided by the square of the sample size. So in order to do this problem, we don't really do it any differently from what we did the last one. That's what you put in your calculator. Just like we did before. From 15 to infinity with a mean of 14, standard deviation of 2.2, divided by the square root of the sample size. This is the only thing that's new, is dividing by the square root of the sample size. And the probability is a whole lot smaller. So that's that area right there. Okay? That's the only thing that we've changed. So this is what the central limit theorem says. And you'll be able to, excuse me, you'll be able to finish your last homework after this. Central limit theorem says if x has any distribution with a mean mu and the standard deviation sigma, then the sample mean, based on a random sample of size n, will have a distribution that approaches the normal distribution with the same mean and standard deviation, but the standard deviation has to be divided by the square root of n, as n gets larger and larger and larger. It's more normal for larger samples and less normal for smaller samples, but it still works. How large should the sample size be to permit the application of the central limit theorem? Well, without going through the applet and a bunch of definitions, usually a sample of about 30 is sufficient. Okay? But that doesn't mean if you've got 29, you can't do the problem. But usually a sample of 30 is sufficient. It can be as small as a sample of 2 if your original population was normally distributed. But this one isn't making the limitation that it has to be normally distributed. This says with any distribution. So the bottom line is that as long as the central limit theorem applies and the problem asks you to find probability related to one observation only, like that one trip, keep sigma the same and work the problem exactly like you've been working. But if the problem asks you to find a probability based on more than one observation, in other words, a sample mean, and the most important part of that is the word mean. You find your new value for sigma by dividing the square root of the sample size into the value of sigma you have. And then you work the problem the same way. Nothing changed. Okay? That's really all that means. So we're going to do one application problem, then I'm going to cut you loose. Records say that the packages shipped by a certain trucking company have a mean weight of 510 pounds. Okay, there's my 510 pounds. Standard deviation is 90 pounds. Then it tells you 100 packages are being shipped today. That 100 has to be something. We've got to figure out what it is. What is the probability that their mean weight? the mean weight of 100 packages. That 100 is the value of N. Will be more than 530 pounds. The first thing you always ask, does the central limit theorem apply? Does it tell us they're normally distributed? No. So then the next question we ask is, okay, how big is the sample? Yes, the central limit theorem applies because the sample size is larger than 30. So then we're ready to work the problem. All we need to do now to work the problem is to calculate the standard error which is going to be 90 over the square root of 100 from that. It's going to turn out that your standard error is actually equal to 9. This is mu x bar, not just mu. So 510, 519, 528, 537. I'm not going to label this part of the curve because I'm looking for where 530 is. And it's right about there. And the area greater than would be the area to the right. So this probability is going to be very small. And if I didn't want to calculate out that that was 9, you could have put in 90 divided by the square root of 100. Calculator will figure it out for you. So the probability that the mean weight of the packages is going to be more than 530 pounds per package is going to be 0.0131. Or about 1.31%. Okay? Y'all have a good evening, but have a safe drive home. Looks like it's slowed down right now, but that doesn't mean it's behaving